Okay, so I want to first just finish the example of SL2 yesterday. So remember that in the case of SL2, we explained the center is generated by Categorification element. And then horizontal map identified is with the so it's a simply this is here y, so as two invariant, here y is a plus 1, and h is the center, and this is the row shift. And then we compute the image of omega and this map is plus 1 or y squared minus. And then we computed how this, well, explain how this is going into the homomorphism of this anti-dominant projector. And this we explain it is C of epsilon over epsilon squared. And that time I said omega is into it's a non-trivial multiple of epsilon plus something, then actually the plus something is 0 because if you look at we're looking at a trivial group, so like the eigenvalue of h is just 0 or -2. And so actually this the pointing ends up to be no coordinates. So omega just if you do a computation, it's like you can identify here it sends to a non-trivial multiple of this for a is the common. And now we want to identify this with the covariant ring. And how does it go? So you just observe that here, since omega is nilpotent, so when you look at in this, if you identify everything in this equation, your y is actually your, well, after quotient, it's not to look at the completion of this ring at the ideal y squared is equal to 1. Okay? Because the eigenvalue of y is minus the fixed generalized eigenvector. But what is this? So you think of so if we have the spectrum Cy, think of the and here, and then you map it to the spectrum of y squared. So it's something like it's a double covered at points which are not 0. So in particular, if you look at the completion around y squared equal to 1, then you're looking at the formal neighborhood of y here. So this is like y squared. And on top you have two copies, which corresponds to eigenvalue equals to 1 or -1. So this completion is actually isomorphic to C of y completed at y equals to 1 plus C of y completed at y equals to -1, and then you take a global invariance for x2. Okay, where x2 permutes these two columns. Okay. It's just a adequate rewriting of this, and in this so in this identification, here you're adding a half of y squared equals to 1. But just developed it at each of the neighborhood, right? Here it's around y equals to 1. So you write this at y minus 1 or plus 1, and the y plus 1 goes to 2. So here you get -1 plus y, and from this factor you get 1 plus y. And then when you're doing the S2 invariant of this, so you can make a transfer of the, so you can just pick one of the copy because the other one will get it by symmetry, and then shift the origin and then throw each, and then you get, well, I think I took this one and you identify with just CLH completed at 0. So H is okay. H is minus or y, and I actually use this copy. So is this clear? This is kind of important. Like, how do we go from this invariant polynomial ring, but completed at a regular point, to actually the entire polynomial ring completed at 0. And then now, if under this map, you do your quotient by default. So now, since omega is identified with epsilon, now if you want to compute anamorphism of P of S0, so this is C of omega. You identify it with C of omega quotient by omega squared. So this is the same as this is the same as if you completed this at surface. So the same as you do this completion y as 2 completed at y squared minus 1, and then under this map your omega goes to like then you quotient by the image of squared in this, and after this identification, it actually goes to CH completed at 0 quotient by the ideal H squared. Okay, and then this is the symmetric algebra of the Herman completed at the completion at 0 included or got, and then this is as invariant part by S2 and you take all completion at 0. And so this is the co-invariant.
Right, just can you say who's y supposed to be?
Y is H plus 1.
How did you think the first of all is it? And I can't figure out. So the anamorphism was projection that in the last time there.
Yeah, so the density of epsilon quotient by epsilon squared. But in our math, what is identified in your omega?
And we know it's epsilon. Let's say epsilon quotient by epsilon squared from over to yesterday.
Yes. Well, yeah, like these are just some commutative algebra stuff, but the important identification is this is what we're going to do all the time. I mean, this is what is important in the future.
Wait, the compound here is one-dimensional.
Yes.
I guess it's not a question. I'm just. Why do we need to go to completions to do this?
To have this isomorphism.
To get the bottom equality.
Yes, to get this identification. So like this identification really comes from this isomorphism. The point is we have fixed the generalized the central character. So you're looking at the particular value. Yeah, so like in this quotient, since this is in the block, your central elements screws on the central character, so that's why you're just looking and your rings are tangent, so you're just looking at a formal thing. So you can just look at the complete part around this point. And then you can make this identification. Otherwise, you don't like if you look over this. Well, then you just get one. Well, yeah, it's more complicated. Yeah, for the single block, you don't get the point there. In this case.
But can also prove that partial point in this way.
Yeah, so I will explain that later in a general picture. Here you just get A. You just get C, like the complex numbers. Other questions?
Are there more geometric explanation of this?
Yeah. Okay. So and today I want to, so this is the example I put to you. It shows you like the theorem I announced yesterday. In this particular case, meaning that the center maps trajectory onto this endomorphic ring, and this is the co-invariant ring. And then later we'll see that identifies with the center of the principal block. And today I want to explain a proof of this in general, and we'll use what Alistair taught us like 30 minutes ago. And so we have learned that if you have a finite dimensional representation G, and then you can write the trace map as following. So you have C to the tensor, and then if you identify VW briefly, and this goes to but and if you have a map, if you have an and here you can just plug in your tensor one E2, and then here you choose the identification of that you invite you, and then the junction on the other side, you get that this is data, and this is the map we're sending identity to the view basis. And this is just the calculating between these two. And we learned back lecture, this is the same as trace of N. Okay. And we will use a relative version of this. Which is, so now I can just, instead of C, I can plug in a module N. And so for N, we choose module N. And I consider M second to M tensor B. 2. And then I want to go back to M. And here, here I take for any M, which is an endomorphism of M tensor B. I can do the following. So here I just put in one M, so the same as eta. And here we're going to do to put M on the first two vectors, and then tensor. And then at the end you do M. What this produces you is so you start from F and an endomorphism of M tensor B, and you get an endomorphism of M. And we call it the relative trace with respect to B. So it it's a map from this endomorphism to the endomorphism of M, which is defined in this one. So this is equal to the relative trace. So in the picture language, before this one was, so you had the L, and then when you close it, and now your M is, so this is your B somewhere, and you will, yeah, I didn't go in the right direction, but I didn't go the direction is not important. And but here but now the relative thing is just that you replace F by now your F is multiple from M tensor B itself. And so you just close the directions on B, and you still get an endomorphism of M. So this is this notion of relative trace. And you can check easily that if M itself is finite dimensional. So for this definition, I don't need any finite bits of M. So completely. But if M is finite dimensional, then you first take the relative trace of a certain X, let's say as before, then there was M. And then you can take trace on M of this map. So you just take the trace of this map. It's an analog of M, and this is the same as the trace of M concerning your initial map. Okay. So why am I interested in this? It's because so now so we have the following remarks. So you see that if whenever I can consider this principle P as an angle function on the fiber of geometries. And then we can consider the natural transformation of this and this function. So what is a natural transformation is, as we explained yesterday, it's just for the data of an endomorphism Xm for each object n, which is compatible with all morphisms in the category. And now what this relative trace gives you is just if you take the relative trace of V, and then starting from the natural transformation of this functor, you get a natural transformation of the identity. Right? Because you start from X here, which is the family of Xm, and you end up with a natural transformation of the identity whose value on M is just given by the relative trace of X. And then as we explained yesterday, so by definition, this is the center of the category, which is the same as the center of UG. Okay. So the construction of relative G gives me a map from this Peng Springer, the natural transformation of this functor to the center of UG. But further, I can also do the following. So for each central element of UG, it gives me a natural transformation. Right? Whose action is just so I have a map from center of UG to this, which is just sending to the natural transformation. The value on M is given by multiplication by Z. Okay, so these are G modules, so they tend to talk about multiplication by elements in UG, and since it's in the center, I'll use the G action, so close form. And then using this relative trace construction, I get back to the center of UG. So therefore, I get a map from the center itself. And this map, by abuse of notation, I was still denoted by trace of E. And our first goal today is to compute this map explicitly, meaning that we have Harishanga map, which identifies this with the W. and we'll give an excellent formula for this. But before going there, let me first make another remarks. So, remark number 2 is that you notice that whenever, so if n belongs to the category O, then if you tensor it with a finite dimensional representation, it still belongs to the category O.
In remark 1 was V a geometrical or just space?
V is a finite dimensional representation. Yeah, and all the representations like the tensor geometries.
Is trace D, is this the algebra method?
No. It's a linear network. Okay. So this you can check it easily. For example, we can look at. We'll talk about how this acts on Bernoulli values and then see. And so in particular, so here you can also use this construction to, you can start with objects in O and then you can end in the center of the category O. So good. So this implies this trace V, which repeats if I consider n natural transformation for objects in O, then I end up in the center of O. And then so this construction is very general, but this you can think of it as part of the exercise for Alistair's courses. So whenever you have a bidefined pair of functors between two categories, so EF are bidefined. So bidefined means we consider category functors between these two categories. Between categories, then they are left and right view. So and then you can apply it with the and then here you can define a kind of a trace map like this, which starts from endomorphism, a natural transformation of E, and you end up in the center of B. You can do the same thing for F, and then you end up in the center of C, which is just following the same principle. If you have the X, which is a natural transformation of E, and then you first go like this. Say if E is up and F is down, and you first use this one, and then you put in your X here, and then you go so you have X here. And you go back to 1. So and so this is a general construction which you can do in many situations whenever you have a bijoint pair of functors. But now let's compute this map. This is what I'm interested in. So to explain the result, I need to first introduce some applications. So we'll fix our V finite dimensional representation of P. And I would denote by PV all the weights of V with multiplicities. Meaning that if V mu is non-zero, then mu occurs in the set with multiplicity equals to dimension of mu. And then I define a function, an operation on a function of H is the carton. As follows. So I write, so if I have a function here, I'll write PV star product with F. This refers to the function whose value at the weight lambda is equal to the sum of all the F evaluate a lambda translated by weights with multiplicities. And then I will impose, so we'll put capital lambda equals to the product of all the cores alpha check where alpha a positive root of our G. So alpha check is an element in H, so I can view it as a function of HQ. So this is a particular element of CHQ. In the case of GLN, it's just the fundamental general like this. And then now we can so by the way, all it's telling today is following a very short paper by Bernstein, which is called traces patterns.
What year? What year? When? When? Is
Oh, like the 80s?
it is.
Yeah. No, they're not the 90s. It happened to paper of Soergel, so he gave us the proof of strokes at right. So so this proposition tells us, so at center of UG of the present version. And we want to understand this map. Then so here we have the Hartunda map goes to the invariance in HQ. And then this map, so these are isomorphisms. And so there's a unique map making this diagram commute. And this map is given by the following. So it sends the polynomial f to the following. So you first do lambda, and then you apply the star. And then this will be divisible by lambdas. So you get in other words, you get, so lambda is the generator of the sign part in the circle. So you prove this is well, that's in the science part. Yeah. But I mean, you have a unique sign. It's generated by lambda, so anyway, I guess I'm just trying to say this is what we have, and this is the result.
But is that lambda just multiply? Okay.
This is just multiplication, and then you apply this shift operation to the entire thing, and this divided by lambda. Okay, so I wanted to explain the idea. So we have a candidate map, and you want to show this diagram commute. So let's call this candidate map trace E tilde. And then you need to show for any z in the center. If you do HC of trace E of T, you want it to be equal to trace E tilde of HC. So this is what we want to prove. But you know that both sides will be polynomials on H star. So you only need to prove that they coincide on infinite points. So to prove their evaluation at infinite many lambda time. And we'll consider so third.
shouldn't there's definitely many ways to be discrete because you can have sub-varieties.
I was hoping there's no one on my table, and then there are mistakes. They don't need to worry. So, I need to, so, we'll actually show that, their evaluation as, the following lambda, which is an integral, lambda, such that lambda plus the entire weight set of B is always a dominant integral weight. So this is a set of dominant integral weights. Okay. So this set is finite because B is finite dimensional, and so there's always infinitely many such lambda. And this is discrete. And so if your two polynomials coincide on each set, and then it must be. And so you and the next thing is for such lambda, because any weight in V is dominant, and then using wild character formula, we can check that the finite dimensional representation L lambda tensor B is just the direct sum over all the mu's of L lambda tensor. All these are finite dimensional representations, semi-simple, and use the character formula to check this. Okay, now what are we interested in? We're interested in this thing. And so what I want to do is I want to take the z action on this and try to compute this relative trace. So now, but then now if I take the trace for the action of z on this module, then according to this decomposition, z acts by scalar on simple modules. So its trace will just be the sum of dimension of these modules times the scalar by which it acts. And so this and the scalar the central character of this module evaluated by NZ, which by the definition of Cartona map is what we denoted by chi lambda continued evaluated NZ times dimension of this is the sum for all the way. Okay. But then this is the same as we by the exercise like with somewhere here. This is the same as first taking the relative trace of with respect to V of this element V, and then take it so and then this is an endomorphism of L lambda, and then we take its trace. And so this you apply the same kind of computation. This is chi lambda of this trace V of T times dimension of L lambda. Okay. And now you need just two more ingredients. You know that by the wild character formula, so if you have dominant weights, the dimension of L nu is precisely this polynomial lambda evaluated by mu plus rho divided by lambda of rho. And you know also by that chi of the chi nu, but this is chi nu of V is the Harshana map. The image of V under the Harshana map evaluated at a input level. And then you just replace, so you have this equality, and you replace the dimension by this, and replace the types by this, and you will get the divider, the equality here evaluated. That part I didn't use. How it works.
So can you give an example to illustrate this proposition? Say G is GLN and A to E would be n-dimensional. Is it possible to describe this map more explicitly?
Well, then this, so then this lambda is just the product of xi minus xj for. But this now depends on which representation you
Yeah, I think just first fundamental.
first fundamental.
For example,
Then you have the weight is just omega 1. Then the first fundamental. So
something like that.
so yeah, so it's okay, so it's just B, right? This CM, and you need to fix the weights.
yeah, maybe other example. I'm just not insisting, but just to have an idea how it looks like for simple examples. Maybe so too.
Okay, that's all too. Okay. Yeah, that's good. So f is a function, is a polynomial in A, right? And then I would just do x1 minus x2 minus the function, and then so B, the weight of B if I denote it by epsilon 1, and then what I'll get is okay. So yeah, so actually it's always then what shall I do? I shall shift this by. Yeah, I think I cannot do it on the work, but I can do it for like once. Need to set up notation.
So in that second line, we use the transitivity of the traces and then final lambda. Is that trace V Z? Does that depend on lambda? Like that's an endomorphism of lambda. So
This is an endomorphism of lambda, yes.
yeah, and then in the second line, and then move across the equality, the first term of the chi lambda and then trace V of Z. Does that trace V of Z depend on lambda? Is that like that thing's in endomorphism of lambda? But is like should there be a lambda there, or is that independent of trace? Like the thing inside have it.
No, trace V of V is just an element in the center. So it's the image of this in the center. This doesn't depend on lambda.
Okay.
And then I evaluate the action of this on.
There are eight theory explanation of the formula.
What theory?
This can I somehow prove this formula in K0 of the black variety?
No, for the moment there's no flag red. We still have, and my time is like. Okay, not very good. But. Alright, so let's go to categorical. And what we're going to do is so on the category O, there's plenty of important functors which are translation functions. Which basically, whenever you have two weights that you mu, such that their difference is the integral weight. So you know that T is kind of all the integral weights. And then you have the golden weights instead of opposites. So we take B to be second dimensional module with external weights. Just the W orbit of the shape. And then you can construct the following functor. So as we explained, tensor with a finite dimensional representation sends O to O. But here you have a block along the inside O. And since it's a direct vector, you can also project. So you can project it to the block here. So it's and you get a functor from number 2 mu like this, and this is the translation functor denoted by T and W. And so you can translate that using EU instead of B. And since here B tensor with B and EU are Fourier twice, it's fixed. So you get a pair of Fourier functions like this. And you can play the game you are interested in today, like applying trace operators to the diagram functions. And then so maybe two important things about this translation functor is that so first of all you can use tensor identity, which means if you tensor a Bernoulli with B, so Bernoulli is an induced module, so it's usually the tensor identity tells you that it's the same as UG. You induce C lambda, but you view V as a B module. With this tensor product. And then you induce. And from here you can see that this thing has a filtration by Bernoulli whose highest weight is lambda plus mu for mu weight. So this has Bernoulli filtration. With factors and so this is kind of important, and you'll use it all the time when you study translation functors. Yeah, and then we apply translation functor only to those which belongs to the block. Your block menu is not very well shown. Okay, and then how are we going to use this? Is we're going to use the following form effect. So we're going to consider the translation from the minus rho block to the regular block 0. The minus rho is the center of the shifted action. So this is any simple category. So here and minus rho is equal to, it's a simple and it's a projective. And when you translate to O0, so then you get, so what you get is actually the anti-dominant projected W0. So first of all, because it has a letter joint which is exactly center projective, and then you can check that by using this thing that the Bernal vectors which appear here are at precisely 0 once. And then you need some extra argument to show that this is but this is the thing we're going to need. So the point is you obtain the anti-dominant projective as a direct vector of n minus rho tensor of that kind of representation. And that is how we're going to use to compute the anamorphism of this ring. And in the 3 minutes, which I have, I will announce the main theorem, which I thought I would be able to prove today, but so right, so the main theorem. So this is responded in the paper that well, originally the result of this formulation which says the natural map from the center to the anamorphism of W to this antidominant projective is rejected. And its curvature can be described as follows. So it is given. So right. So if we identify the splits, the is the position of the Harshana map, the inverse of the Harshana map with this action map. So we call this A. And then the kernel of A is invariant polynomials with the following property that a map B I'm going to define will kill at the ideal generated by that. And what is this map B? It's defined as follows. So B is a linear map from C W to C, which sends a function f to the sum over elements in the well group of T. So this I will explain later. Lambda is as before, so it's product of coordinates, polycoordinates, and this is the shift motion by lambda. So here T TW rho is just you shift the function from CHQ to the function of whose value at lambda is equal to f of lambda. Okay, so right, so you take the sum of all these shifts and then you divide it by lambda and you evaluate this thing at 0. So this is this map B, and the plane is the kernel is given by all the functions whose ideal vanished, with the ideal generated by which vanished. So here you are just seeing some similarity with respect to the proposition I explained here. Because that one was you shift by all the weights in B of lambda f and then divided by f lambda. Here I only shift those in orbit of rho because I'm projecting to the regular orbits. So after the project only this makes orbits. So and so this is the description of the kernel. And then furthermore you can show that the quotient of kernel determined by the kernel of A, it's isomorphic to C of HQ that quotient by C of H star quotient by the multiplication idea. This is the covariance. So this is a similar isomorphism as the one I explained for SLQ at the beginning. And then, so from from all this, you can deduce that the endomorphism of P of X0 about 0 is isomorphic to the covariance. The time is up, so